One more thing that we need to consider is that we have different types of systems. All the systems we've looked at so far have had one solution. Let's look at what happens when we graph this system, y equals 5x minus 5 and y equals 5x plus 1. There are the graphs. Of course, they have the same slope, therefore they're parallel. If they're parallel lines, they'll never intersect. If we try to calculate the intersection point, there's our first curve, there's our second curve, our guess doesn't matter, and we get an error because, of course, there is no intersection point. Therefore, there can be no solution to this system. This system is called an inconsistent system because it has no solution. Let's see what happens when we try to solve this inconsistent system algebraically. It's already solved for y, so it's set up nicely for substitution. So we'll take this 5x minus 5 and substitute it for y in the second equation. We get 5x minus 5 equals 5x plus 1. And so, getting our constants together, we have 5x equals 5x plus 6. Getting our variable terms together, what happens when we subtract 5x from each side, we get 0 equals 6. The variable drops out of the equation completely. Now, when that happens, there are a couple of possibilities of what that might mean. In this case, we get 0 equals 6, which is false. We know that this is a contradiction. And so that means this equation can never be true. Therefore, this system that gave us this equation can never be solved. It has no solution. It is an inconsistent system. Here's another example. If we try to solve this system, it's nicely set up so that we can apply the elimination method. So we're going to go ahead and multiply by a -3 on both sides. What's going to happen is our first equation will stay the same. Our second equation will become -6x minus 9y equals -18. And when we add these two to eliminate the variable, the x is eliminated and the y is also eliminated. On the right, our constants end up being eliminated as well. So once again, the variable has dropped out of the equation, but we don't get a false statement this time, we get a true statement. We know that this is an identity. Now what that means for the case of the one variable equation is that it would always be true. Or in other words, every real number would satisfy the equation. That means every real number can be an x value that solves the system. The same thing's true for y. Every real number can be a y value of a solution to the system. However, not every point is going to be a solution to the system, even though there will be an infinite number. Let's look at the graph to see what the solution looks like. Before we can look at the graph, of course, we're going to need to rewrite our equations in slope-intercept form. So here, we'll have 9y equals -6x plus 18. Dividing by 9, we get y equals a -2/3 x plus 2. For the second equation, 2x plus 3y equals 6. We're going to have 3y equals -2x plus 6. Dividing both sides by 3, we get y equals -2/3 x plus 2. Notice the two equations are identical, which is why we ended up where we did. And so when we look at the graph, what we're going to see is that the two equations give us the same line. Here is the equation of both lines in slope-intercept form. We graph it, and there it is. This is really both of the lines overlapping one another. That means that every point on this line will be a solution to the system, because every point on this line is a solution to both equations. See? However, points off the line, such as points up here, will not be solutions to the system because they are not solutions to either equation. The question then becomes, if there are an infinite number of solutions, but the solutions are not every point in the plane, how do we write the solution set? Well, we know the solution set consists exactly of the points on the line represented by both of the equations. So the answer is to use set builder notation. It is going to be the set of all ordered pairs xy such that the following property holds. X and y are related by this equation. If this equation is true of the pair x and y, then that xy pair is a solution to this system. And we don't have to use this form of the equation. We could use either of these as well, or any other equivalent form. It doesn't matter. So we could say this. Because these two equations represent the same line, these are the same solution set. Here's a quick summary of what we've just been saying. Here are three types of systems we can have. If the system represents lines that intersect once, then that one intersection point is the solution. The solution set is that one point. The system is said to be consistent because it has a solution, and the equations are independent. The second type is if we have parallel lines, then they never intersect, so there is no solution, zero solutions. The solution set is the empty set. The system is said to be inconsistent because it has no solution. But the equations are still said to be independent because they don't represent the same line. The third type is if our two equations do represent the same line, then there is an infinite number of solutions. The solution set is the set of all points, fill in the blank with the equation of the line, so all points that lie on that line. The system is consistent because it has a solution. In fact, it has an infinite number. The equations are called dependent because they represent the same line.